Yeah, so the course basically it kind of breaks into three different topics, and those three topics sort of, each of the tests kind of focuses on one of these topics in some sense. So I've kind of broken up the course in that way. The first topic is enumeration, and enumeration, that's just a fancy word, of course, um, for counting. So a typical question in this part of the course is going to be, how many ways can you, so on and so forth. So fill in the blank, right? So how many ways can you do this? How many ways can you do that? And I want you to be able to, count different things. So like I said, this is the topic of the first test, and that test is going to be on February 11th. So that's what we're going to spend the first several lectures on. Second topic that's going to start after enumeration is, I'm calling this combinatorial structures, meaning sort of an introduction to different types of things that you see in combinatorics. So the main one is going to be graphs. So what is a graph? A graph is just something like this. Basically, when I say graph, you should think network. It's a bunch of points where some of the points are connected by lines. Right, this is the main structure we're going to focus on, but we'll also talk about a few other things as well. And the test for this is on March 18th. But yeah, you don't need to worry about that yet. The third topic is going to be generating functions and recurrence relations, which is, I'm not going to tell you, exactly what that is yet, but basically it's about analyzing sequences of numbers. So some of you may have heard of the Fibonacci sequence, for example. So it's the sequence where you start with a 1 and a 1, and then each element of the sequence is the sum of the previous two elements. So 2 is 1 plus 1, 3 is 2 plus 1, 5 is 3 plus 2, 8 is 5 plus 3, and so on. So we're going to learn about how to analyze these types of sequences. And that's going to be way in the future, near the end of the course, and that's going to be on test 3, or test 3 is going to be on this topic, and that's going to be during the exam period. So that's a brief overview of the course. Let's now get into the first topic, which is enumeration. And by the way, if you have any questions at any point, you can write them in the chat. Like I said, you can unmute yourself or whatever you prefer, whatever works for you. Okay, so two of the important ideas in enumeration are the rule of product and the rule of sum. So let's start with the rule of product. So it's all very intuitive, but it's still important to think about it. So if suppose that there's X different ways that you can do one thing. So thing here, it's all a bit informal, but suppose there's X ways of doing one thing and Y ways of doing another thing. Then how many ways are there to do both of those things? Well, there's X times Y ways to do both. So that is the rule of product. Okay, so for an example, suppose I roll a red die. So a die, like a dice, one of these things. So suppose I roll a red die, and then I flip a coin. For the die, there's 6 different outcomes. For the coin, there's 2 different outcomes. How many outcomes are there for the whole thing? Well, if you go through and count them up, you'll see that it's pretty clear, right? It can be 1 in heads, it can be 2 in heads, 3, 4, 5, 6 in heads, or 1, 2, 3, 4, 5, 6 in tails. But really, you don't have to write all this out. You can just use this rule of product to say that there's 6 outcomes for the die, 2 outcomes for the coin. So the answer is going to be 6 times 2, which is 12, right? So this is a really simple example. We're going to be doing things that are much more complicated than this, but this is just to show the idea. So when you're ever doing one thing and the other, you're doing the rule of product. So actually, maybe I'll emphasize that. So the rule of product, often when you see a question and it has the word and, if you're doing something and something else, and you want to know how many ways there are to do it, it's usually a product. Okay, I won't say always, just to be safe, but usually it's rule. Rule of sum is it's a bit weirder to explain, but it's not complicated. So suppose that there's x different ways of doing one thing, y ways of doing the other, and this is the part that's a bit confusing, but suppose that it's not possible to do both things at the same time. So you're gonna do one thing or the other, but you never do both. So how many ways are there to do one or the other? Well, it's going to be x plus y, because there's x ways to do the first, y ways to do the second. So basically, if you look at all the ways to do something, you have x ways to do the first, y ways to do the second. You never do both of them. Yeah, I don't know how to explain it better than that, but intuitively, it's going to be x plus y, right? As an example, let's think about some dice again. So suppose you have two dice in your pocket. One is red and one is blue. Okay, and let's say that the color matters here. What you do is you stick your hand in your pocket, you pull one out, and you roll it. Okay? How many different outcomes are there? Maybe I'll put that to the audience. So, yep, thanks. So 12 outcomes because, yeah, basically there's 6 outcomes. There's 6 outcomes, which for the red die, plus 6 for the blue is 12, right? Yeah, that's a good analogy. X ways to stand up, Y ways to sit down. You can't do both. So how many ways are there to either stand up or sit down? I guess it's going to be X plus Y. So these things, like, they sound really simple and trivial, but when you get into more abstract problems, the difficult part is really to understand which of these rules you should be applying at what time. Okay, maybe. Oh, here's another one. This one I like. So, counting the complement. So, suppose there's a certain number of ways to do something, but you don't want to count all the ways of doing that thing. You just want to count some special examples of, right? So you want to count, well, there's an example here, but basically sometimes it's easier to take the total. So if you can count the total number of ways to do something, count the ones you don't want to count, and then subtract them from the total. Sometimes that's easier than directly counting what you wanted to count. So this example says, how many ways are there to roll a red die and roll a blue die so that the sum is not equal to 3? So if you're trying to count, there's lots of different possible sums, right? It can add up rolling two dice can add up to any number between 2 and 12, right? And you wouldn't want to go through all the possibilities and just count up all the ones that aren't equal to 3. It's easier to count the ones that are equal to 3, right? Because, the only way to get a 3 is to have a red 1 and a blue 2, that adds up to 3. Or you can have a red 2 and a blue 1, and that gives you 3. If I counted all the things that don't give you 3, that would take me a lot longer. So the answer is, so what you want to do is you want to look at how many different outcomes are there. So by the rule of product, there's 6 outcomes for the red one, almost 6 times 6, yeah, right, exactly. So by the rule of product, you've got, rule of product tells you 6 times 6 total possibilities, and then you throw away the ones you don't want, and there's exactly these 2 of them, so 34. Right, so take all the possibilities in the universe minus the ones that you don't want to count. So that's just a useful kind of... Okay. Any questions about anything so far? Right, like I said, the rules themselves are not hard. Knowing when to apply them is really going to be the hard part. Yeah, so what I want to talk about now is strings. Okay, so first I need a few definitions. So I'm going to let square brackets n denote the first n positive integers. So the numbers 1 up to n, where n is a natural number. And people sometimes use the natural numbers different ways, including 0 or not. Just to be clear, for this course, the natural numbers are always going to start at 1. So if I have x and y are sets, a function f from x to y is an assignment of each x in x to some point f of x in y. So I guess this is probably familiar to you, but just to refresh your memory. Oh yeah, okay, so an example of a function. So if x is the set 1, 2, 7, y is the set a for dog 24. If I let f of 1 be, let's say, 2, f of 2 be 1. Oh, sorry, that doesn't make any sense. F of 1 be a, f of 2 be dog, f of 3 is a, then f is a function. So this is from x to y. Okay, so it assigns, we'll get into that, but the answer is no. So there's a question about whether strings have to be one-to-one, and the answer is going to be no. Okay, so here's what the definition of strings. So let n be a positive integer or a natural number, let x be a set, and a string with alphabet x is a function, let's say s, from the set square brackets n to x. Remember, n is the numbers 1 up to n. Okay, so that's the formal definition of a string. We're usually not going to write strings in this kind of function notation, but this is the formal definition. The elements of x, so x is the alphabet, right? And the elements of x are called characters or letters, or yeah, symbols perhaps, basically whatever. Also strings are sometimes called words. Okay, so to address the question, so strings don't have to be one-to-one, so you can use the same letter many times. Okay, so we normally, so yeah, strings, you can write them as a function, but so for each integer I, you have some element si, but we're usually actually going to write them a little bit differently. We're going to write it as s sub I, just because, I don't know, that the notation's a bit nicer perhaps. And also, we're not going to specify a string by writing s1 equals blah, s2 equals blah, s3 equals whatever. It's a lot easier to just concatenate the symbols, right? So writing s1 first, s2 second, all the way down to sn in order, right? This is how you think of a word, right? This is what a word is. You just take letters and you write them one after the other. But yeah, it's also useful to think of things formally, mathematically as well. Okay, so if I write A, B, A, C, 7, alpha, for example, this is a string of length, well, yeah, so the length of the string is the length of the string, the number of characters. This is a string of length 6 with alphabet. The alphabet might not just be these letters, right? The alphabet can be A, B, C, D, 6, 7, alpha, at symbol, and whatever. So that is a string of length 6 with this alphabet. Okay, so a few very easy. So everything in this first lecture is going to be very easy. Trust me, though, it's going to get harder after this at some point. But yeah, this is all just kind of a warm-up. Oh, if the element in the alphabet was, say, XY, would that be one letter? Yeah, that's a bit annoying. But yeah, if your alphabet contains XY, then yes, XY would be one letter. It could also contain X, and it could also contain Y, which then kind of screws up the whole concatenation notation. But let's just say in this course that's never going to be an issue. Yeah. So I'm always going to ask you questions where all of the symbols are distinct single letter symbols. But Okay, so what is the length of this string A, B, B, A, C, 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 A, which is annoying because I have to count 1, 2, 3, 4, 5, 6, 7, 8, 9. Does everybody agree it's 9? I think. Uh, okay, so so suppose S, so this is the type of notation we'll use, right? If I just write S equals C, C, B, B, A, C, B, that means S is the string. S is this string. So what is S5? Any guesses? It's good that I've got these guesses coming in because I suck at counting apparently. I thought it was C, but you're right, it's A. So fifth letter is A. I mean, this kind of feels a bit like kindergarten right now, but yeah, okay. So binary string, so some special types of strings. Binary string is a string with alphabet 0, 1. So for example, if I take 0, 0, 1, 1, 0, 1, that's a binary string. Ternary string has alphabet 0, 1, 2. So if I ever say the word binary string or ternary string, you know what it is. Okay, so now a counting question. How many strings of length, let's say k, are there from an alphabet of size n? So I claim that the answer is n to the k. Okay, and this goes back to one of these rules, right? So if you think about it, how many strings of length n can I make, or sorry, length k? Well, let's just think about it letter by letter, right? So for the first letter, you can choose any element of the alphabet. So n choices for first letter, right? And once I've chosen the first letter, I can choose the next letter however I want, right? So I again have n choices for the second letter, and the third letter, and so on, and I have n choices for every letter. And when you're choosing a string, you can think of it as choosing the first letter and the second and the third and the fourth, right? So remember when you have this and going on, you have the rule of product. So the number of choices is then n times n times n times n, k times, which is n to the k. So this is the rule of product. Yeah, I'm going to go with, so the question is a binary string always, does it always have alphabet 0, 1, or can it be any set of 2 elements? I'm going to go with, like, if no other explanation is given, then it's 0, 1. But to be honest, I'm never going to mark you down for, doing things in terms of 1 and 2, or x and y, or any other, as long as the answer is right, I don't really care what the symbols are, but you should always expect it to be 0, 1. Okay, so the English alphabet has 26 characters. How many 5-letter strings are there? Oh, yeah, that's just how Zoom works, I think, in terms of the delay. I don't think I can really do much better than that. Maybe I should write and then say it. Yeah, I can delay my speech. Yeah, so the number of 5-letter strings, so by the thing we did on the previous slide, we have 26 different characters, right? And it's 26 to the 5 because, yeah, 26 choices for each character. So suppose you live in a province where you've got license plates where they have 3 letters followed by 3 numbers. How many possible license plates are there? So maybe I'll give this to the audience. Okay, yeah. It would be 9 times 9 times 9 if you don't allow 0. But I think you've got the concept. Yeah, so 26 cubed, 10 cubed. Yeah, I always forget whether 0 is a number or not. Maybe when I ask these questions in the future, I should always put, a digit between 0 and 9 or something. But okay, so hopefully that's clear. Okay, yeah, way to visualize it, but I think most of you kind of got it. But yeah, in the future, you can visualize things this way, right? You have, 20, you can kind of think of it as, I don't know, columns with, 26 choices for the first column, 26 choices, 10, 10, 10, right? And that can apply to a lot of different questions. Okay, this is a little bit trickier one. So how many strings of length 5 can you make? Sorry that the writing here is a bit ugly. Where the ith letter is in the first I letters of the alphabet. And again, it's just rule of product, right? I've got how many ways can I choose the first letter? Well, it has to be in the first 1 letters of the alphabet, so it has to be A, right? So I've got one way to choose the first letter. It has to be A. The second can be A or B because it has to be in the first 2 letters of the alphabet. So I've got 2 choices. You've got A, B, C, 3 choices, 4 choices for the next one, 5 for the next one. Okay, so this is again the rule of product. But this doesn't follow from what I said before about choosing a string of length k from n characters, because there we had no restriction, but here we have a restriction that they have to come in the first I letters of the alphabet. Yeah, and this is going to be 5 factorial. I haven't told you what factorials are, but that's coming next lecture. But yeah, for those of you who already know what factorials are, this is indeed 5 factorial. Okay. Yeah, website passwords. So suppose you have a website that requires every user to have a password of length 6, where you're allowed to use lowercase letters, uppercase letters, and numbers. Right? So remember, there's 26 lowercase, 26 upper, 10 numbers. So we've got, how many is 62 different characters? But you have a restriction. The first character has to be an uppercase letter or an even number. How many usernames are there? I'm just throwing small curveballs in there as we go. That sounds right. Yeah. So you got that, I guess, by, the first one has the number of choices for the first one is, it can be either an uppercase letter or it can be an even number. So that's the number of choices for the first letter or the first character. And then the rest of the characters had no restriction, so it's just 62. Yeah, that's right. Again, rule of product. It's a real product, but also kind of inside of here, inside of the first letter, it's kind of the rule of sum. Actually, they're all kind of the rule of sum, because when I came up with this 62 by taking 26, 26, and 10, the first letter has, or any letter has to be either uppercase, lowercase, or a number, and it can't be all of them, right? So all of these were kind of rules of sum, and then at the end, you put it all together with a rule product. Any questions about this? How many 7-digit numbers are there in which any 3 consecutive digits are all different? Oh, wait a sec. And all digits. I think I've made the same mistake somebody did before. Well, let's just say all digits are between 1 and 9. Okay, so after I've chosen the first digit, how many ways can I choose the second? Yeah, exactly. I'm not allowed to choose the same one as I did before. The next one, I can't choose either of the ones I chose before, and those are both different. That's kind of important, right? Yeah, so now it goes down to 7. After that, though, I again have 7 choices, because I can choose any of the 9 digits except for the one that came here and the one that came here. 7, and then 4, 6, 7. So it's 9 times 8 times 7 to the... Okay. So these are just, yeah, tricky kind of applications of this, this rule of product. And yeah, like I said, there's so many different questions I can ask like this. And there's a lot of different questions in the practice problems and stuff like that, and you're going to see this in the assignment. Basically, like I said, using the rule, when you know which rule to use, it's usually not the hard part. The tricky thing is finding out which rule to use at what time. Okay, so like I said, there's a whole bunch of practice problems in the textbook. Um, so how many of these 2n digit positive integers, odd positions have to be odd, even positions have to be even and positive? Yeah, it's the number of digits is even, and in particular, it's equal to 2n. So, um, so I guess this should say at the beginning, kind of for some n, or or for any n, for n in the naturals. Like for every different n, we want to for every n, it's going to be a different answer. Yeah, so we've got some answers coming in. I think the wording is a bit. That's actually one thing in these problems is that just kind of sometimes the questions are quite long. Like you see number 3 here is extremely long. Um, and just understanding the wording is kind of part of the problem here. So we've got different answers coming in. They're all the types of answers I would expect. So the answer is actually, yeah, 5 to the n, 4 to the n. I think. I might even be getting this wrong. Uh, so where this comes from is the 5 to the n is for the odd positions. So the odd positions can be any number 1, 3, 5, 7, 9. The even positions must be even and positive. That's kind of and 0 is not positive. So 0 is not positive. In case anyone thinks it is. It's not negative either, but it's technically not positive. So the even positions each has 4 choices, so it's 4 to the n, right? You have n odd positions and even positions, and there you go. Okay, so yeah, part of the battle here is just going to be understanding what the question is asking. Okay, any questions about anything from the lecture or about the course or anything? If not, then maybe I'll end this early, and I'll see you guys on Thursday.